Imagine you've just been handed the keys to a brand new, highly advanced AI system for your organization.
Oh, the dream scenario, right?
Right. I mean, it's powerful, it's lightning fast, it costs your company an absolute fortune to build, and absolutely no one wants to use it.
Yeah, they run the other way.
Exactly. Your staff is actively avoiding it. So, why do so many of these massive, well funded tech transformations just completely fail when they actually hit the real world?
It's honestly the ultimate paradox of the enterprise tech age we're in right now.
Yeah.
Organizations will spend all their capital perfecting the mathematics, building the infrastructure, training the models, and then they completely forget about the human
For the
beings.
people who actually have to press the buttons.
Yes, the people who press the buttons and, crucially, trust the output.
And that is the exact mission of our deep dive today. We are looking at this fascinating stack of training materials and slide decks covering data analytics and AI for healthcare, along with enterprise AI tools and project implementation.
It's a lot of material, but really good stuff.
It is, and our goal is to extract the blueprint for successfully bringing AI into the real world. We aren't just talking about cool algorithms today. We want to dive into the messy human reality of project scoping, building the right team, and, getting fiercely independent stakeholders to actually buy in.
Because, I mean, if you fail at the human element, the most sophisticated machine learning model in the world is basically just a very expensive paperweight.
A very expensive, very complicated paperweight.
Exactly. And in high-stakes environments like healthcare, it really all comes down to a fundamental lack of trust.
Okay, let's unpack this, because starting with the end user makes so much sense to me. The core reason these projects fail is that stakeholders are terrified of what they call the black box.
Oh, absolutely. They have no idea what's happening inside it.
Right. A veteran doctor is not going to change a patient's treatment plan just because a computer screen said, hey, trust me. Before an organization can even build the AI, they have to know how to explain its internal logic.
Yeah, and the sources highlight that overcoming this massive resistance, transitioning from traditional practices to AI, it requires a specific framework called explainable AI. And they break this down into three strict pillars.
Okay, what's the first one?
So first, there's explainable data. If you're presenting a model to a hospital board, you have to be able to answer what specific historical data was used to train this model and why.
Like, where did it come from?
Exactly. Was the data set actually comprehensive, or was it, skewed toward a specific demographic that might make it completely fail in the real world?
Which brings us to the second pillar, which is explainable predictions. When the AI makes a specific call on a specific patient, what features and weights did it actually prioritize?
Right. The why did it choose this part?
Yeah, like if it flags a patient for a high risk of readmission, the doctor needs to know if that flag was triggered by their age, a sudden spike in blood pressure, or just some weird anomaly in their chart.
And then finally, the third pillar is explainable algorithms. And this basically means cracking open that black box to understand the individual layers and the actual mathematical thresholds the system used to arrive at that prediction.
I like to think of AI in healthcare like a brilliant but just incredibly secretive medical student.
Oh, that's a good way to look at it.
Right, because it doesn't matter if that student gets the diagnosis right every single time. If they can't, show their math and explain the biological pathways they analyze to get there, the attending physician is never going to sign off on their chart.
No, of course not. A brilliant diagnosis without a visible methodology is clinically useless. And if we connect this to the bigger picture, an algorithm's value is absolute zero if it doesn't align with strategic organizational goals.
Meaning what exactly?
Well, a hospital's goal isn't just having the flashiest new technology. They measure success through KPIs, like reduced readmission rates or shorter patient stays.
The things that actually impact the hospital.
Right. Plus, you are operating under monumental regulatory hurdles: PDPA, GDPR, ICHIPA. Patient data confidentiality is completely non-negotiable.
Yeah, you can't mess around with that.
You really can't.
Yeah.
If your system can't definitively explain how it's stripping identifying markers and protecting that data at every single layer,
Yeah.
I mean, the project is dead before it even launches.
So building this explainable, highly regulated system is so complex that, you obviously can't just lock a bunch of coders in a basement and wait for magic to happen.
No, the lone genius coder is a myth here.
Right. You need a highly specific, multidisciplinary team to build and translate the tech.
And the sources outline 5 core roles that really need to be in every data science team. just start with the data scientists,
Right.
obviously.
Hmm.
They handle the heavy statistical lifting and the scripting to actually find the insights.
But a model on a laptop is useless.
Exactly. So you need the ML engineer. They handle the software engineering and DevOps. They build the actual infrastructure that allows the data scientist model to process, 10,000 requests a minute in the real world.
Okay, got it. Then the sources mention an information designer, which is someone focused on visual and interaction design to make those outputs readable.
Vital for communication. Yeah.
And then a data science manager to kind of herd the cats and handle change management. But here's the one I really want to push back on.
Okay, let's hear it.
The fifth role is the data translator, who handles domain expertise and business analysis. I mean, is a data translator really necessary?
You think it sounds like corporate fluff?
A little bit. We are always trying to cut corporate bloat. Isn't this just a fancy title for a middleman? Like, why can't the data scientist just walk down to the ER and talk to the doctors directly?
Because they literally don't speak the same language. A clinician understands the nuanced life and death reality of patient care, right?
Sure.
So a doctor might tell the data scientist, hey, we need to know when a patient is going to crash. The data scientist takes that, goes back to their desk, and literally searches the SQL database for a column labeled crash.
Oh, wow. And obviously that doesn't exist.
It doesn't exist, so the model fails.
Okay, but paying a whole separate salary just for a translator seems excessive. Can't the project manager do that?
Well, no, because a project manager tracks timelines and budgets. The translator bridges a massive technical chasm. They know enough SQL and scripting to understand the actual database constraints, but they also know enough about clinical workflows to know that nurses don't have time to enter data into 15 different manual fields.
So they're keeping it grounded in reality.
Exactly. They ensure the final product actually solves a tangible clinical problem, rather than just being a mathematically impressive model that actively annoys the medical staff. And they are the ones constantly looping in domain experts, like the actual clinicians, to test the reality of the model.
Okay, that makes a lot of sense. But if you are building this multidisciplinary team, how do you even know if these completely different specialists are actually good at their jobs? I mean, a resume only tells you so much.
You have to measure their capabilities across several distinct axes. You administer technical skills assessments using platforms like HackerRank or Codility, but, and this is key, you don't use generic coding tests.
You make it specific to the job.
Right. You tailor the scenario specifically for healthcare data challenges. And you look at hard performance metrics over time, like the accuracy of their past models and their time to deployment. But crucially, the sources emphasize evaluating their collaboration quotient.
Collaboration quotient. How do you even quantify collaboration?
By looking at how they work within the system. You assess how they utilize team collaboration tools like Trello or Asana, and this is a big one, how they document their code so others can read it.
Oh, like leaving notes for the next person.
Yeah. A data scientist who builds a genius-level predictive model but completely refuses to document their assumptions or communicate with the ML engineer.
Yeah.
They will tank the entire multidisciplinary project.
Okay, so let's say you've hired this expensive team. They are functioning beautifully. But if they have to build a complex diagnostic AI entirely from scratch, writing every single line of foundational code, you'll run out of funding before they finish. How do they bypass that blank page problem?
They utilize a really powerful technique called transfer learning. It's essentially a method for AI to mimic human learning by reusing existing structural knowledge, instead of just starting from zero for every single new task.
Okay, walk me through the mechanics of that.
Let's use a visual recognition example from the sources. Say you want to build an AI to classify images. You start by training a convolutional neural network from scratch. You feed it thousands and thousands of images of cars.
Just endless pictures of cars.
Endless. And the system spends massive amounts of server time and computing power just learning the basic visual features of a car, like what an edge is, how curves form wheels, how shadows work on a windshield.
So it's basically learning the basic geometry.
Yes, exactly. Now, let's say tomorrow your organization decides they need an AI to classify trucks. Instead of spending millions of compute hours starting from nothing all over again, you take that pre-trained model. You freeze those foundation layers that already understand edges and curves. You transfer it, and you only fine-tune the top layers of its network weights on a much smaller dataset featuring trucks.
So transfer learning almost sounds like letting an AI copy its older sibling's homework.
Kinda.
Is there a risk of it learning the wrong lessons if the problem domains aren't perfectly matched?
Well, it's less like copying homework and more like, learning the grammar of a language before learning new vocabulary. But you've hit on the exact risk you have to manage. The pros are undeniable, right? Faster training, drastically less new data required, and significantly lower computing costs.
But the cons.
The cons are very real. You risk something called overfitting, where the model learns the new data too well and loses its ability to generalize. Like, if the original model was trained on sunny photos of cars and you feed it snowy photos of trucks, it might just fail completely.
Oh, because it associates the object with the weather?
Right. It gets confused by the context.
To structure these specific AI tasks, the sources talk about using an AI business model, Canvas, and they give a really detailed example of an AI designed for comment moderation on a hospital's public forum.
Yeah, the Canvas forces the team to map out the entire life cycle mechanically, which is so helpful. First, you ask, what is the input? In this case, user comment text. Then, what is the prediction? The system calculates the probability that the comment is appropriate or inappropriate.
Then there is judgment, and this is fascinating to me because it's entirely about operational trade-offs. The Canvas forces the team to ask, do we prioritize reducing false negatives, meaning we accidentally let some highly offensive comments slip through, or do we aggressively reduce false positives, where we accidentally flag a genuine, innocent patient question?
And that judgment phase leads directly to action, which is automatically flagging the comment for a human or maybe hiding it instantly, which finally leads to the outcome. Maintaining a healthy online environment while reducing the manual workload for human moderators. If you don't map that out step by step, the AI might just aggressively delete everything, and your patients revolt.
Honestly, this sounds a lot like triage, which brings up the next massive hurdle. The team has the tools, like transfer learning, to build fast, but resources are finite. Time, money, server space, it all runs out.
It always does.
So how do organizations actually decide which projects get the green light? If you're the one managing this budget, it really is like triage in an emergency room. You don't just treat the coolest looking injury. You assess feasibility, urgency, and resource availability.
Yeah, you have to prioritize systematically for maximum return on investment. The financial factors are strict. You have to ask, what are the projected costs for securing the data, paying for the cloud infrastructure, and the staff hours?
The hard numbers.
Exactly. What is the time horizon? Are we looking for a quick operational win right now, or a 5-year strategic benefit? And what is the actual payback period?
And to figure that out without just, guessing, the sources recommend using decision matrices. You essentially plot potential projects on a visual graph.
Right. You plot value or opportunity score on the x-axis against risk or complexity on the y-axis. This creates 4 distinct operational quadrants.
How do you use those quadrants?
Well, if a project is low value and high risk, you abandon it immediately. If it's low value but low risk, you do case by case. If it's high value and high risk, it's a need to do, which is like a long-term strategic bet that requires really careful planning.
Okay, what about the last one?
The sweet spot is high value, low risk. Those are your must-do projects. You fund those today.
Okay, so once you pick a must-do, how do you keep the project from turning into a chaotic money pit?
You rely on the CRISP-DM methodology. It stands for Cross-Industry Standard Process for Data Mining. It operates in 6 very structured phases: business understanding, data preparation, modeling, evaluation, and deployment.
Walk me through the friction there, because data preparation sounds like, I don't know, spending an afternoon organizing a few spreadsheets.
Oh, I wish. In reality, data preparation takes up to 80% of the project's entire timeline.
Wait, really? 80%?
Yes. It involves spending weeks or even months cleaning up doctors' messy shorthand, dealing with totally inconsistent medical billing codes, and handling missing patient records before the AI can even look at the data.
Wow.
And what's fascinating here is how the CRISP-DM framework is circular. It visually forces the team to continuously loop back from evaluation straight back into business understanding.
But it's not just a straight line.
No. It actively prevents the data scientist from building tech in a vacuum. If the model during evaluation accurately predicts patient flow but doesn't actually solve the ER bottleneck, the framework forces you to go back to the drawing board.
And you execute this through agile delivery, right? Like you don't disappear into a lab for a year and just hope the hospital still needs the tool when you emerge.
Exactly. You work in 1 to 4 week Scrum sprints. You're testing and iterating constantly with the frontline staff. And along the way, you also have to make heavy structural decisions about your computing power.
Like where it lives.
Right. Do you use the cloud for flexibility and rapid scaling during a crisis? Do you build on-premise servers because you need maximum localized control over sensitive records? Or do you use some kind of hybrid model?
Okay, let's say we did it. We built the perfect model, we prioritized correctly, we used CRISP-DM, we deployed it on the cloud, the AI works flawlessly. But we are still not done because the final, arguably most critical step is getting the human beings in the building to actually act on the data.
The hardest part.
It is, because if the communication fails, the entire project fails.
Yeah, you have to translate complex analytical results into understandable, actionable insights, and you really have to tailor those visuals to the specific stakeholders staring at the screen.
And the sources give really precise examples of this customization. Like, if you are presenting to hospital administrators, you show them cost-effectiveness graphs.
Yeah.
They need to see budget allocation and resource efficiency.
Right.
But if you show that exact same cost graph to a clinician, they will completely ignore it. A clinician needs visual summaries of patient outcomes post-treatment, or time series charts showing a patient's specific recovery trajectory.
Exactly. And if you are presenting to the board members, they don't want the granular details. They need high-level dashboards showing hospital-wide metrics. Public health officials, on the other hand, they need geographic heat maps highlighting disease prevalence across an entire city.
So it's all the same underlying mathematical data.
Yes, but translated into the visual language, the specific user actually needs to do their job.
Here's where it gets really interesting, though. I want to challenge this idea a bit.
Okay, go for it.
If the algorithm's predictions are highly accurate, let's say we have a wearable device that accurately predicts a heart irregularity before a patient even feels it. Doesn't the data just speak for itself? Like, if it demonstrably saves lives or saves money, why do we need to dress it up in a fancy infographic for the administrators or the doctors? They should just look at the accuracy rate and adopt it.
This raises an important question, but honestly, that is the exact trap that tech teams fall into, and it's exactly why projects fail.
Really?
Yes, data never speaks for itself. Human beings interpret data, and human beings come with institutional habits, professional pride, and deep-seated fears.
So the psychology gets in the way.
Completely. The sources clearly point out that a major operational cause of failure is simply resistance to change. Stakeholders may fear obsolescence. They worry the new system's there to replace their expertise, not just the system.
So if you just drop a predictive spreadsheet on a veteran doctor's desk and say, hey, the machine knows best, they will reject it out of professional pride and, frankly, a genuine concern for patient safety.
They will actively find ways to bypass it. Furthermore, there are massive operational risks regarding data hallucinations, where the AI confidently provides mathematically flawed information.
Which happens all the time.
It does. And if stakeholders don't understand the AI's limitations, they develop wildly unrealistic expectations. They either think the system is infallible, which is very dangerous, or the first time it makes a mistake, they think it's entirely useless and refuse to ever log in again.
So how do you break through that resistance?
Tailored communication builds operational trust. You have to prove the value through small, contained proof-of-concept pilot programs. Let one specific department test it and become champions for the software.
Start small, win them over.
Exactly. You have to translate the tech into the specific financial or clinical metrics they care about. And most importantly, you have to invest heavily in upskilling and reskilling your staff. You must foster a culture of continuous learning so people feel empowered to command the tool rather than feeling threatened by it.
So what does this all mean? We've covered a massive amount of ground today. We started with the necessity of explainable algorithms to conquer the fear of the black box.
A huge hurdle.
We broke down the friction within a multidisciplinary team, especially why that data translator is so critical for bridging the gap between coders and clinicians. We explored mechanical shortcuts like transfer learning, the rigorous triage of project prioritization using decision matrices and CRISP-DM, and finally, the psychological necessity of communicating visually to win over skeptical human stakeholders.
We've basically charted the entire nervous system of a successful enterprise tech adoption. It requires just as much organizational psychology and workflow management as it does actual computer science.
It really does, and it leaves me with one final kind of provocative thought based on everything we've unpacked.
I love these. Let's hear it.
We spend all this time, capital, and energy constructing these explainable AI systems to perfectly mirror and assist human judgment. But what happens when the AI does its job perfectly and reveals that our historical human data, our past decisions, our operational workflows are actually deeply flawed or incredibly inefficient?
Oh, the uncomfortable truth.
Exactly. When the machine shows us our own ugly operational reflection, will we actually have the organizational humility to let the AI correct us? Or will that deep-seated human resistance to change cause us to just reject the very truth we asked the machine to find in the first place?
I mean, that is the ultimate operational test of any data-driven organization.
Something for you to mull over the next time a dashboard tells your team something you really didn't want to hear. Thanks for joining us on this deep dive.